Hello everyone, it's my great pleasure to give a presentation here. I'm Anran, research fellow from the Nanyang Technological University. My topic here is the efficient federated learning model debugging. And it was 1 week that was accepted by the IEEE ICD 2021. And I will introduce my our work from the following outlines. The first, I will introduce some background. First, we all know that the federated learning enables a large number of mobile local clients to jointly construct a global model without sending their private data to the remote server. And this provides some privacy preserving about their local data and saves the bandwidth. And the data sources in FL are various, such as through the crowdsourcing or through the web crawling. So the quality of data are various, and the low quality data leads to serious consequences. Here we give some experimental results to validate that the local awareness data results in low performance global FL models. And in the x-axis is the mislabeling ratio, that is the mislabel, and the y-axis is the test accuracy. And we can see that with the mislabeling ratio increase, the test accuracy decreases accordingly. And so towards awareness data in FL clients, we aim to propose an efficient data-based model debugging or interpretation for federated learning. Here, the model debugging means the giving explanations of model prediction results. And first, I will give some existing works of the model debugging. There are two branches. The first is in the centralized learning. In centralized learning, the model debugging use through the perturb subset of the data sample and to see the prediction, the change in the test results. And the other line analysis, the influence of data samples on the model's predictions. And in the federated learning, there's the work that focuses on the client level, that is the client level contribution to FL models. And but there are some limitations of existing work, like in the centralized learning, that is to direct access to data, and it also will cause high computation or high communication cost, and it will also since that is to direct access to local data, it will cause privacy concerns. And in the federated learning scenarios, there's only just the client level contribution analysis or client level analysis, but there is a lack of efficient sample level or sample-based model debugging interpretation methods for FL models. First I will give the problem description. We assume that there are two roles of the participants, the server S and the local clients. With the coordination of the server, multiple clients collaborated to construct a global model. And since there are some erroneous samples, such as the mislabeled ones, and also there are qualified samples, and due to the erroneous samples used to training the global model, there would be some prediction test errors, or it would result in the low performance global models. So our aim is to identify the erroneous data of the local clients, and we aim to propose an efficient federated learning model debugging from the perspective of data. Also, we assume that all participants in this scenario are semi-honest. And first, I will give an introduction of the influence function for FL, which was used to develop our system. Influence function was used to approximate the effect that one sample was removed from the training, how large the parameter change or global model change when we remove one sample zki from client ck. And the direct way is to we just remove this sample from the training and retrain the model. It was very expensive, and the influence function was proposed to avoid retraining the model by providing a first-order approximation to the actual effect. And the influence function was quantified by the following equation. It was composed of three components. The first component is the gradient of the training loss with regard to the global model. And the second part is the inversion of the Hessian metric. And the third part is the loss is the gradient of the test loss with regard to the global model. And as we can see that, to calculate the influence of one sample zki, we have to compute the inversion Hessian and the gradient of its sample. And since the inversion Hessian was hard to compute, its computation is very expensive and would cost larger communication cost. And in this way, in this work, we propose two methods to largely reduce the computation cost for the influence function. But with the influence function, we have the following two insights, which motivates the system of our design. The first insight is that the influence function has an additive property when measuring the change in test predictions. That is to say, the influence value of one client can be calculated by summing up its client's samples influence values, and by this insight, it enlightens our hierarchical influence analysis. That is, we can identify the influential clients first to save large cost for sample level influence analysis. And the second insight is that when there are more qualified training samples than the erroneous ones, erroneous samples have obviously larger absolute influence values than the qualified ones. And this can be shown from the following figures. For example, like the left of the finger, there are 150, the first 150 samples are mislabeled. And we can see that their influence scores or their influence values are much larger than the qualified ones. And use this insight, it gives us an opportunity to distinguish erroneous samples and erroneous and the negatively influential clients that have erroneous samples from the qualified ones. And now I will introduce the challenging issues and our solutions. To identify the erroneous samples or the negatively influential clients, we have to protect the data privacy. That is, to this end, we propose a hierarchical influence analysis. And the second point is that the local clients have restricted resources like the communication cost or like the communication resources or the computation resources, and to To make this system efficient, we propose the training log-based method in the hierarchical influence analysis. And the third is that the FL system can be heterogeneous. That is, some clients might have limited communication resources, and other clients might have limited computation resources. So we hope this identification method should be adaptive. And to this end, we propose two identification methods adaptively. And next, I will introduce our system design. The system consists of two main components. The first part is the hierarchical influence analysis. In this part, we first identify the negatively influential client. That is, the negatively influential client means the client that have erroneous samples. And for those negatively influential clients, we further identify their erroneous samples. And in this way, we can save a large amount of computation and communication costs. And after we identify the erroneous samples, we can retrain the model to achieve a high performance model. And during the retraining process, we propose an influence-based client selection method to accelerate the model convergence to generate a high performance global model. And next, I will introduce this system in detail. The first part is I will introduce the basic method of client identification, and after this, I will introduce our proposed training log-based client identification. The basic method of client identification is that influential clients have obviously larger absolute influence values than qualified ones. We can see from the following figures. As for the figure A, we can see that the first 30 clients possess mislevel data, and we can see that these 30 clients have the larger influence scores than the qualified ones that do not have the erroneous samples. And since the client's influence values are calculated by summing up the influence values of all its samples, so it gives our one way to distinguish the negatively influential clients to the qualified ones. But directly using this method would cost a large amount of computation and communication cost, since there is one need to directly calculate the inversion of the Hessian matrix and all the training gradients of all its samples. So to reduce the large computation or large communication cost, we propose a training log-based client identification method. Here, the training log means the training log is stored on the server, and the training log is that in each training round, the local client would use his local data to produce his local model, and this model will be sent to the server. And the local model parameters is the training log here. Yeah, and that we know that a client is negatively influential if his distance, that is, if his local model's distance is significantly greater than the median distance of all other clients. That is, we can use the distance means that his local model's difference from the global model. And here is the empirical observation. You can see that client zero is the negatively influential client, and his differential updates or his distance from the global model is much larger than the normal clients or than the qualified clients. And use this way, we can distinguish the negatively influential clients from the qualified ones. Just use the training log which was stored on the server. And also in this way, we can dramatically save both computation and communication cost by orders of magnitude. And since the training log is stored on the server, so there's no communication cost for client identification. And after introducing the negatively influential client identification method, I will introduce the sample identification. And first, I will also give the best method for the sample selection. And as I introduced before, that a sample is negatively influential if its influence value is significantly greater than the median influence values. We can see from these pictures. The first 150 samples are errors, or the mislevel ones, and their influence scores are much larger than the normal samples or the qualified samples. But directly, if we directly calculate influence values for all these local samples, it would cause acceptable cost. Since we need to calculate the training gradients for each of the local sample, and we need to calculate the inversion of the Hessian matrix to calculate the influence values of each local sample. And to reduce this high computation or communication cost, we propose two efficient methods. The first method is computation efficient sample identification. That is, we use Hessian vector products (HVP) to approximate the inversion of the Hessian and times the test gradients. Since the original directly calculated method is the third power of t, and but we can reduce it to OP. That is, we first use the Taylor expansion to expand the original the inversion Hessian matrix, and then we use the Monte Carlo sampling to approximate these products. So in this way, we can much reduce the computation cost. And for the communication cost, we can use the batch to decrease the communication cost. That is, we do not need to sample for every samples gradients, but for the one batch. In this way, we can reduce the communication cost. And here is the complexity analysis. Using the HVP method, we can reduce the computation cost into ONT and the communication cost into ORP. We can see that the complexity is greatly reduced. And for the scenarios that clients communication results limited, we propose a communication saving sample identification. That is, we will use the calculation of this product as the minimized optimization problem, and we can use sample one cut at each step to recursively approximate the X2 and to approximate the inversion of H and times V. And in this way, we can also reduce the computation cost to ONT and reduce the communication cost to OKH. And until now, I have introduced the identification of negatively influential kinds and his erroneous samples. And use these identification results, we can retraining for a better model. And in the retraining process, we can also further use the influence-based pattern selection method to accelerate the model convergence. That is, we dynamically select clients to participate according to their influences, and we assign clients with larger influence on the current global model with higher probabilities. And in this way, we can achieve produce a high performance model that has a higher test accuracy and faster convergence model than the previous one. And now I can give some privacy analysis during model debugging. The first, there is no local training data transmitted during training, debugging process, and updating process. And during our debugging process, the parameters we transmitted is the second order information, so it cannot be used to infer the local training data. So our debugging method preserves the privacy of local clients and achieve a high performance global model. And next, I will introduce the evaluation of our proposed method. The first is our system deployment. We deploy our model debugging method into a real-world testbed. It consists of one server and 50 local clients. The clients can be laptops, edge nodes, or the desktops, and they communicate with the server through the socket. And the datasets we use here are image datasets and audio datasets. And also, there are many FL models, and there are different things of different FL models. We can see that there may be some 9% mislabel ratio of local samples, and there are some negatively influential clients among the whole clients. And first, I will give the results that the proposed influence function for FL gives the correct approximation to the original leave some out retraining. We can see that the x-axis is the actual difference in loss, and the y-axis is the predicted differences in loss that was calculated by the influence function for FL. We can see that the predicted influence and the actual changes in losses are correlated with PCC equals 0.6. And the next, I will give the result that our proposed training log-based method can correctly identify the negatively influential clients. Yes, we can see that client 0 is a negatively influential client, and others are qualified clients. And we can see that the training log-based method calculates the differential updates that are much larger, larger than the other qualified clients. And we can choose the accuracy, precision, and recall of the identification method equals 100%. And here, also there's a threshold here. Its threshold is set up to 1.5 in our experiments. And also, there is the computation cost and the communication cost in the training log-based identification method. We can see that the computation cost is much higher. It's much is much smaller than the other best two methods. These best two methods are calculated by summing up the influence values of all its samples. And since the training log is stored at the server, so there's no communication cost for this training log-based method. But other methods have very high communication cost. So using the training log-based identification method, we can save both computation and communication costs by orders of magnitude. And after identifying the negatively influential clients, we further identify their negatively samples or their erroneous samples. From the left figure, we can see that the first 100 samples are erroneous, and here they are the mislabeling samples. You can see that their influence scores are much higher than the other qualified ones. And these influence score values are calculated using our the first algorithm, that is the computation saving the computation efficient sample identification method. And here is the accuracy, precision, and the recall of our identification method. We can see that we can achieve fairly high accuracy in all settings. And here is the efficiency comparison. We compare the computation cost and the communication cost of our HVP-based influence calculation method with the original retraining method. We can see that the costs are orders of magnitude lower, both in the computation cost and the communication cost. And further, we conduct the large-scale simulations. That is, there are 1,000 clients. There are 1,000 local clients in this FL systems. And we can see that the model debugging method is scalable and robust in these larger environments. And next, we also conduct the larger scale simulations for different mislabeling ratios and for different non-RD scenarios. And it can also be seen that it is scalable and robust in large environments. And finally, I will give a conclusion. The first, we present the framework FL debugger to accomplish both debugging and interpretability of FL models from the perspective of training data. And the second, we design a hierarchical negatively influential class and sample identification method with around 90% accuracy. And the third, we design an inference-based client selection retraining method to facilitate the model training in terms of high accuracy and faster convergence. And that's all my talk. Thanks for listening.